Dorn is an inspiration to me in his sharpness and creativity when it comes to regenerative agriculture. Dorn wears many hats. Among these, he is a founding member and board president of Farmhack, an open-source community for resilient agriculture. He is also the executive director of Green Start and manages his family's 250-acre organic farm in Lee, New Hampshire. Dorn builds systems for small-scale grain and oilseeds processing, biofuels production, and no and low-till equipment and practices. He is a founding board member of the New England Farmers Union, the Great Bay Grain Cooperative, the Oyster River Biofuel Initiative, and he serves as a vice president of the New Hampshire Association of Conservation Districts. He is close to receiving his PhD from the University of New Hampshire in developing open source agricultural research and improving farm productivity and resilience. Again, his work is an inspiration. He is going to present today on soil and silicon, open source tools for a regenerative agriculture. Please welcome Dorn Cox.
It's really terrific to be back here. I was here 3 years ago, and it was one of my favorite trips, one of the most wonderful communities, exploring these topics that I've found anywhere. So as Kate mentioned, we're gonna talk a little bit about agriculture. And when I was here 3 years ago, we talked more about what we were doing on the agriculture is really the culture of the field. And last time we talked a lot about the field part of it, the technology and the approach that we're using to try and build resilience into our soils through a lot of diversity. Today we're going to focus more on the cultural side, looking at some of the complexity that we're managing and trying to add that diversity in to start to build some of that resilience into our agricultural systems. And I thought the Back to the Future theme this year was especially appropriate and something that I think about a lot, in that we're often looking back to techniques that have fallen out of fashion, are no longer appropriate to the current industrial scale, or have just never been adopted in our region or in our culture. And so we're both looking back and using also the network of tools, the silicon portion that's linking people in right now in a way that's never been possible in human history. It's really a fantastic time in human history in some respects, in that we can connect with every other human on Earth, essentially, and we can contemplate everything from the smallest microbes up to global climate and biogeochemical systems. And so I put up here as the starting slide this balance of Back to the Future. We're looking at a couple different systems. We're looking at how are we harnessing these systems that were the evolutionary systems, biological systems that have had millions of years to evolve, and we're just exploring how to understand that. And some of that's happening because we can now sequence the genomes, we start to understand it. But what we're not doing yet is understanding the larger context of how they all work together. And so that's where it comes into, and we haven't really had the capacity to do that until just recently, and we'll get into that later. The other image here is just 5,000 days old. This is a image of the internet. And what's interesting about this is that Silicon Valley thinker Kevin Kelly says it is approximately right now about the complexity of the human brain. And it's going to double every 2 years. And so that's what we're just starting to see. And so we're at a crossroads. How do we apply this complexity to this other problem of looking at managing our soils? Looking at this system is not new. We took a turn at some point during the Industrial Revolution to start a deductive process of looking at all the details and figuring out how systems work. But if you step back, again, this Back to the Future, just 200 years ago, the approach to science was very different. You didn't have a body of knowledge, scientific knowledge to draw on, so you had a systems-based approach. So you had to observe a lot. Of course, at that point, there wasn't a lot of tools to do that. But what they did do during the Enlightenment was start to document all of the tools. And one of the byproducts of the Enlightenment was an open source, crowdsourced encyclopedia, about 2,000 contributors, and it was one of the most published books at that time. And it wasn't just that they were trying to get it out there. This was part of an initiative that they thought was important for the good of mankind, and that it not only covered arts and sciences, but most importantly, to the talk the rest of the day here, is that it covered mechanical arts and agriculture and cooking and metallurgy and all the things that you need to do. And I'm going to read a little quote from the editor. And he says, "The goal of the encyclopedia is to assemble all the knowledge scattered on the surface of the earth, demonstrate the general system to the people with whom we live, to transmit it to the people who will come after us, so that our works, centuries past, is not useless to the centuries which follow, and that our descendants, by becoming more learned, may become more virtuous and happier, and that we do not die without having merited being part of the human race." So that's why I bring this up before we start talking about agriculture and open source, because that is the root of the values associated with open source, is that cumulative knowledge for the benefit of mankind. And so when we start, and this seemed like when we started Farmhack, we didn't have this background. It seemed like a crazy idea. And then we start digging back and say, in fact, this has a deep history in agrarianism, especially, partly because it's so complex that you need cooperation. And so what you have on the right here is documentation of a small grain mill, which is particularly interesting because it's one of the first things that our community in Farmhack that we'll talk about in a little bit was clamoring for. We need a smaller grain mill so we can mill for our local markets. So, as I mentioned, they're also systems thinkers, and because science there wasn't such a thing as a scientist, which the scientist wasn't as a concept, or as a word even, wasn't invented or used until 1830s. And that came along with the deductive art of research and industrialism. So at this point, it was natural philosophy, and it was systems thinking. It meant that if you were interested in agriculture, it was also looking at economy and ethics and philosophy. And so they're really looking at the big picture. And so in doing so, they came up with some pretty good observations, I think. And as an agrarian culture at that time, there were also particular values that they were pushing, recognizing that, and they become, out of this came the physiocrats, which means governance of nature, and their key beliefs were that the wealth of nations derived from the health of the soil, and the only way to increase the wealth of a nation was to improve the health of the soil, and everything after that was a transformation of that original wealth. And that's pretty important. So it's a land-based economic system. And that persisted until partway through the Industrial Revolution, when suddenly the folks who were managing the capital saw that there was an imbalance in power. And in fact, there was a concerted effort, which is not, we won't get into it, but essentially to erase this idea that land is a factor of production and switch it that capital is much more important than land. And so one of the well-known physiocrat, again, governance of nature, this idea that we can understand nature and we can make it better. That's another important thing that we've lost. We just think of land as a static resource. They were very much in tune with this, and that it took social conditions as well as mechanical and technological approaches to improve it. Mirabeau, Marquis de Mirabeau, prior to the French Revolution, wrote this, and I've put a graphic representation of it. And he's saying that the state's a tree, agriculture its roots, population its trunk, arts and commerce are its leaves, its roots come the sap drawn up from fibers from the soil. The leaves, the most brilliant part, arts and commerce, And so when we hear that agriculture is a business like no other, or like every other, this is arguing absolutely not. It is fundamentally different from every other business because of this root function. And this persisted until relatively recently, and again has been erased. Even on the Department of Agriculture, this is some variation of this, was that agriculture is the foundation of commerce and industry. But if we're talking about resilience, this is a model that we're talking about, and if you're communicating this, it's that everybody has an interest in improving the root structure. Everybody essentially, this is sort of the definition of agrarianism from there at this point. So why is this relevant? Well, again, this if we're talking about the values, the power associated with this is really important. If agriculture is just a subset of commerce, then you have different values associated with the care of that resource. And you head towards an extractive cycle where commerce has greater scale and capital can lead to greater extraction. If you're focused on land as the primary resource, then you're going to invest in it. And so that's essentially the paradigm we've been in, and we've talked a lot about this, is that we've degraded our soil resources as human-based soil degradation. But as we just talked about, we can also improve it, and that's such an important piece to bring back into the conversation. Otherwise, we end up with what we are right now, which we have this large culture built on a very small root system that is not resilient. So how does that relate to what we're talking about today, silicon and communication and computational power, complexity? So this is also taken from that encyclopedia. It's just on I won't read it all, but I just picked 1 month of the prescription for what you might do for 1 month's labor. And so we're talking about an extraordinarily complex set of tasks that's going on as far as ecosystem management. And every month is at least this complex. And January would be a relatively slow month in the middle of France. So if we're thinking about precision agriculture and maintaining these systems, think about, and that we have more computational power coming online, wouldn't it make sense to apply it to manage some of this complexity to get some of the long-term resilience and benefit? And so that's a little bit what we're trying to do, although in nowhere near as complex our systems on our farm are nowhere near as complex yet. But I just put this up here just because we've got ivy growing on the Ethernet cable, and we've got we're looking back with the horse, and we're moving forward with our mechanized biofuel equipment. But that this is a blending of this, and we're just starting to be able to take advantage of some of that technology to manage the complexity. And we'll just go through some of the diversity that we're trying to implement: multi-cropping, grazing, multi-species, cover crops, more animals, high tunnels, and building diversity into our markets as well, both wholesale and direct market, CSAs and restaurants, grains, all part of rotations, and all the equipment, figuring these systems out. This is where we're adding complexity. Creating our own fuel on site adds another level of complexity to managing the systems, but also adds to resilience. Garlic. So here's some no-till annual forage into roller-crimped winter rye, all organic no-till. So here's an example of some of the complexity, again, that we're facing, and where we're barely even touching the surface, is that the complexity that they were working on 250 years ago, they didn't have the benefit of the tools to understand a lot of the systems that we now do. So the rate of change was much smaller. So, for example, they were talking about Jethro Tull 50 years earlier, having done a really interesting single plot, but it wasn't replicated, so they were going to have to wait for another generation, somebody to please do that. And so they were talking generations, but we have the ability now, by connecting to folks and other folks who are working, to start to sort out all the possible interactions between complex cover crops and plant and root and animal interactions in different structures, warm and cool season, different below ground and above ground structures. This is the task. And so that's where you come to the modern open source movement that's blossomed partly because of the last 5,000 days of the internet. And a lot of it, you may well know, is run on open source software. So you're familiar with Wikipedia, Apache, Mozilla, but this trend has been really accelerating. And so about 3 years ago, there were only a few thousand open source projects documented. In the last year, there were 1 million documented, and it's going to be 2 million this year. So it's accelerating. You've probably heard that Tesla is not going to be defending their patents. And I just heard, I think yesterday, that Microsoft is going to make .NET open source. So this is a trend, and there are a lot of reasons for it. But when we're dealing with trying to build dependability and robustness and resilience, it just makes sense to collaborate and share the risk and build on others' accomplishments rather than heading in our own directions. And I would argue that agriculture is exactly the same way. If we want to build complexity in, we can't have folks going entirely, well, here's the beauty of open source. People can go off on their own direction, but then there's an ability to bring that back in and communicate and patch it back in. So with all that long introduction, Farmhack came out of this as essentially a modern approach to try and replicate some of these ideas.
Farmhack is a farmer-driven community to develop, document, and build tools for resilient agriculture and to build community around that goal. For the last 50 years, mainstream agricultural research and development has tried to solve farmers' problems with top-down, chemical, capital, and energy-intensive machines. The kind of equipment we want is affordable, adaptable, appropriate, and easy to fix. Because of the lack of such equipment in the marketplace, many of us use old equipment or create working prototypes that we fix and adapt for our uses. The Farmhack community was founded in 2010 by a group of startup farmers working to fill the gap and a way to build capacity in our movement for the manufacture of appropriate tools. Inspired by the many individual efforts for inventive design and adaptation, we wanted to create an organization for community-driven design with more feedback between projects. We wanted to team up with non-farmers who have relevant skill sets and build new relationships in our local economies. We bring our community together both in person and online. In our first 2 years, we've hosted 10 community events. Attending are farmers, engineers, designers, architects, and other allies who brainstorm solutions and collaborate together on the farmers' projects. As an operating system, the Farmhack community is built on open source principles. The platform is built on Drupal, and the community and all products of it are available to and editable by all. It is horizontal exchange of information and mechanical ideas. On the website, you can contribute or learn from a forum or the tools wiki. The site works because users document the tools they've made or modified. This creates a directory of innovations and ideas to build from. Each tool is described using links, videos, components, and schematics for works in progress or functioning prototypes. You can even offer polished products as kits for sale. Because Farmhack is an open source community whose success is driven by the needs of its users, our growing strength comes from users like you. We hope you will join the Farmhack community. Join in the spirit of open source, of mutual aid, appropriate technology, mechanical innovation, and regional manufacturing and fabrication of good tools for good farms. These are the values and tools that fit the ethics and systems of our sustainable farms and the new economy we are building together. Come hack with us at farmhack.net.
So we launched that site, I think, about 2.5 years ago, just after I was last at Quivira, and it's been built almost entirely until this fall on volunteer labor. So all the products of it truly were by the community. We've had over 200,000 folks visit it. We're several thousand contributors. We have 200 tools that have been documented, 600 conversations that have started. So we're just now being able to start to get that feedback to really improve it and be able to handle the additional traffic and pressures that come with that growing community. But I think it's really important that this project is including not just the farmers, because I think if we're trying to address these larger issues in education, I think that's where we come back to that tree. It's so important that it's not just about farmers, it's about communicating these complex systems and value for the entire citizenry. And that, for example, when not to go back to the age of the Enlightenment, Darwin wrote extensively about how he worried about his work not being accessible enough and really worked to try and get some of his friends who were better writers to write popular versions. And he said that popular treatise may be much more valuable than even great original work, because part of the job of the scientist and of agriculture is to involve everybody in that. And so when we're talking about hacking, it's partly rejecting the specialization that we've gotten into that's resulted in consumer dependence, and looking at products not as end products but as projects, and that can be adapted and improved by the community. So, and the other interesting thing with this, as it gets complex and spreads out, is that the production model, inventors are increasingly not the end users of the product. It quickly evolves, and the ultimate use may be something entirely different. But most important is that, again, it's a starting point, it's a social process, and we're involving, as we saw in the video, all sorts of folks coming together, working on trying to build a better agricultural system. And very importantly, that social aspect, so that we're documenting online, but that we're connecting with folks outside of agriculture as well as with other folks. And that's where it's been really terrific to work through the Young Farmers Coalition, who was really who actually hosted the very first Farmhack at MIT. But this, again, is not a new idea, this idea of the community club. This is taken from 1918 Encyclopedia of Practical Farm Knowledge, put out by the Sears and Roebuck Foundation. So if you think about the printing, the Encyclopedia of 1751, now we have 1918 Agrarian Culture putting out a similar book distributed through the best distribution mechanism of the time, the Sears and Roebuck catalog. So very clearly, open source ethic involved in agriculture. The community club being the heart, and the farms and community around it are receiving from all ideas and giving to all ideas and information and inspiration. So looking at that chart, it's observing the soil, integrating it into their farm, bringing it back to the community club, and circulating those ideas through. So not a new idea. We have new technology to do iterate faster and to have better tools to understand those natural systems. So it goes back even further. If you think about the process, the open source process of domesticating seeds, if you think about a bean, what you do when you select a bean is capture the code that's appropriate that you want, and you can hand that to somebody, they can replant it, and they're constantly improving. This is essentially an open source process as long as you have viable seed. If you don't have viable seed, if you're producing sterile hybrids, that whole process stops. So this process can also be replicated with physical objects. So essentially, here we have a diagram of the evolution of helmets. You start with a Viking helmet, and you end up with jousting helmets in the middle, and so on and so forth. But what's important, and what we realized as we were going through Farmhack, was that when you're talking about open sourcing hardware, it's still just software. It's really the blueprints. It's the code that you need to be able to reproduce it. You need to document how do you go about reproducing these objects, and it has an evolutionary component to it. So the outcome of the website, we can see this happen. So the Rodale Institute in let's see, I think it was 2006, released a roller crimper design, which is meant to kill mechanically annual cover crops that you can then no-till directly into. The photo in the bottom left there is we purchased one. There's a commercial operation in Pennsylvania that started manufacturing them, but they published the designs. We posted those on Farmhack. The other designs, I believe, are in Quebec and Germany. These are more iterations that happened in Germany, again, within, I believe this was within a year or so of the first release, and then more iterations the following year. And so these actually, two of those are in France, one's in Pennsylvania, and we're building one on the upper right, and there are folks in upstate New York that are starting to build these. And they're each improvement's based on the application. So we have some that work for really good, nice flat fields, others for corn, others for raised beds, but the same basic principle. And this is what's important as we look at this system, that the tools we use are really a reflection of our understanding of the biology and our environment and how we approach it. So it's not that the roller crimper is the tool, it's that you need a method to crimp the stem, because at a certain flowering time, it's susceptible. So it's that deeper understanding that goes along with it. It's not just selling the tool. So it's also important when we're looking at scaling to appropriate operations, and we can, there's a lot of knowledge all over the rest of the world that we haven't had access to. So part of what we've been doing with Green Start, for example, is to look for examples in other parts of the country, bring them in, test them out, document them, and get them in use. So for example, in New England, we haven't had grain production really since prior to the Civil War. That was prior to the sickle bar mower. So we never built any infrastructure, and we can grow grain very well. But our topography doesn't lend itself to modern commercially available combines. So these are all various versions from Asia, and they've worked fantastically well. Oat huller example is another example. We can bring with documentation, unlike extinct animals, we can bring them back. So here's the manufacturing instructions. We found original engineering drawings for an oat huller that's appropriate for on-farm use. We can now digitize them and send them to a local manufacturer, build prototypes from them, and then we can also share those designs anywhere on Earth, and we have now more and more local precision manufacturing that can use that code to turn out parts. So that, for example, 3D printers. But as I mentioned, it's not just about the farming, it's also the manufacturing and building a resilient infrastructure that supports that. So when we're looking at this idea that we can have every farm be adapting and be a research farm and contributing to this, we also are talking about neighbors being manufacturers to create those tools. But it's not just heavy welding either. We're also, with the proliferation of inexpensive electronics, we're also doing a lot of electronic hacking and feeding that into our environmental monitoring system. But again, it's not just about the tools, it's about this understanding, and that's what this is about. So we're looking, we need to develop a system, and this is part of the next stage, that isn't focused on the tool, a piece of steel behind a diesel tractor, but that there are substitutes, that we're trying to solve a biological problem that a tillage radish might do just as well or even better, because it's storing nutrients for the following year and breaking up compaction and providing winter cover. So, and with that comes the process of involving the community in testing and trialing and reducing the risk of any one producer by spreading it out and communicating the results. So a very simple image like this can go a long way, but it needs to be accompanied with all the detailed associated information. What happened that was significant with those results? That's where it comes into documenting, on-farm documentation. One of the first projects was a greenhouse. A farmer came to a Farmhack event and said, I've lost frequently my crop in the greenhouse. In the spring we had an unusually hot day, and I was down the road, I didn't catch it in time. So is there something that you could do with available technology to alert me to it? And so one of the first projects was a simple text message alert for greenhouse temperature. But because those schematics were published, it was almost immediately translated into an electric fence alert, and then a watering alert. And then we realized, oh, well, once we're going that way, some of the new open source hardware is getting more sophisticated and less expensive, and a company popped up and said, well, we can make open source hardware boards, and we can do lots more. We can data log. We can also make those data logs available over the internet. You can change those parameters over the internet, and we can hitch it up to monitor other stuff. We can do soil moisture. We can do rainfall. We can operate your fans. We can open your vents. All that can be added on. And so there's the expanded concept. So that gets into, we can manage with it, but if we're actually also recording all this data, we can communicate that to our neighbors and other farms and make what we're doing that much more valuable. And so this is the Apatronics wireless remote sensing next to our greenhouse on our farm. So that gets into sort of this next phase of the conditions that are partly made this possible and affordable. So when these are all observational technologies, which I think are fundamentally different from some of the other tools that we use. It changes our perspective about how we go about what we're doing. It's an educational tool for us, and when we communicate with others, we have some common sense of how we fit in our environment. That's why I think this blue dot image is so important. But a lot's happened. We instead of one image, now we're starting to get huge amounts of imagery coming in that we can use to manage and understand our effect on our landscape more. I mean, that's where we finally have some sense of biogeochemistry, and we have some CO2 numbers. We're starting to realize the situation we're in. But this has been the realm of governments and large corporations as far as having access to this kind of data. And that's where I think the open source movement is also important, because some of the trends that we've seen are a dramatic reduction in the cost of storage, processing power, imagery equipment. So they all follow essentially the same trend, which is getting close to zero, the cost of communication. And so the most modern example we have right now is in everybody's, or most folks' pocket. We have smartphones everywhere. There are going to be 2 billion of these things in operation next year. and it's heading up. We're at, 40% connectivity right now, and it's heading up. Each of these devices has lots of remote sensors already built into it. But we're really focused right now on, how does that affect our app, and does it, dim when we have it close to our head? But if you turn it around and you start pointing it out and aggregating that data, we have a pretty high-resolution remote sensing system already. It's GPS, accelerometer, microphones, compass, gyroscopes. There's a lot in there, but we're not really using it to monitor and improve our understanding of our environment yet. It's just a sense of where we're headed. And it's interesting, here, this is a map of internet connectivity to date, and it's interesting, most of our contributions from Farmhack around the world are where we have high concentrations. So as that concentration extends, the network will logically extend as well. So where we're headed with this, I think, is that we went from the cost of observation being really high, not very accurate, and very exclusive, to a position where we had governments able to access it somewhat accurately, but not very accessible and not many people involved. So from a process of understanding and changing values and understanding environmental systems and appreciating agricultural function and ecosystem services and all the things that we talk about here, being able to get more people involved in monitoring is pretty important. So again, using the technology to monitor and position our activities within that framework, that agrarian framework. And so there's a lot of things that we can get just from imagery, but as we mentioned with these wireless sensors, there's a lot more that we can get even without imagery. Imagery just happens to be the least expensive, least invasive way to collect data. But I don't want to focus too much on the technology, because this is still about the social system. The objective isn't to get more and more complex with the technology. The objective is actually to get to where we don't need the technology and we understand these systems and they become internalized, so that we can get rid of it. If we understand the indicators, we understand if we see an indicator plant that really means that we're low in phosphorus, or that a particular kind of algae starts popping up, that we have some other issue, then that's where we want to get. But the challenge is validating that and monitoring it. But and so the idea is this constant improvement. As we get better data, we can have better ecosystem services and better tools and better management. But it involves all of those different disciplines, from economic, social, technological, biochemical, and biological. We can't tackle that with piecemeal interdisciplinary studies. It really has to be this whole systems approach, in my view. And so we've seen a pretty quick iteration from the apetronics sensors and imaging to also looking at water sensors as well, and having them start to talk to one another. Here's a low-cost water sensor that public laboratory is putting out. And that all happened because we started to understand this system a little better. And the lower cost and systems, the more resolution we can get, and the more we can tell these stories and bring, and then go from things that we throw up our hands and say, these are non-point source pollutions, to saying, we actually know exactly where it's coming from, and now we can address it. So we're also doing, integrating that with aerial imagery. This is a low-cost unit that Public Labs is working on to put standard Canon SureShot cameras on weather balloons, put them on kites. And I mentioned that that the technology that we have in our smartphones is also exactly the same technology we need for things like autopilots. So this is an aircraft carrying a camera, $100 camera. All the components of this now, you can build this for less than $500. And it's coming down. The LiDAR system on the right is just $100. That's a new low-cost LiDAR system, if you can imagine. That's going to be $100. So it's kind of mind-boggling, and it's exciting, but it's also fairly terrifying. But I think that's where it comes to the culture that's so important, and that if we don't understand these, this is happening. If we don't understand this, we're going to be controlled by it. And this is, again, just the tip. There was a recent announcement in the UK for a new radio chip that's going to use the spectrum that we gave up from when we stopped using analog TV. It's going to be under $2, have a 5-mile range, and it will last 10 years on a AA battery. That's what they're pitching. So what does that mean? That means we're not having, right now we're talking about smartphones with 2 billion users. It's going to be more. This is where there's a potential for 50 billion sensors out there, and who knows where they're going, what's happening with them. So I think it's really important, if we're looking for transparency, and what do we do with this, that we're aware that there are positive ways to use this, and that we push for that. Otherwise, as I said, we'll be controlled by it. So it can be used productively. So here's the aircraft imaging. And just to give a sense, actually, of the power of this open source system, here's the roughly equivalent, without the software and all the support. The Trimble system is a $60,000 drone. You can buy right now off 3D Robotics site open source hardware autopilot for $1,300. $5,400 if you add the proprietary image analysis software. So this is what, we talked about changing perspective about our operations. This is what we can start to do. So this was taken from a balloon a few years ago. This was just last year. And so we're doing some warm season grass trials. A year ago, or 2 years ago, this is how I would have shown it. You can see switchgrass starting to come up. We can get a sense of the big blue stem is 7 feet tall. But I did trials, and in a few minutes you can start to see patterns and relative densities of the different treatments. You can pick out by color the switchgrass from the Indian grass from where we hadn't treated it. And you step back further and you can see those patterns even more. You can really see the switchgrass starting to jump. So a few years ago we started modeling these systems sort of hypothetically. And this was, I think I did this little diagram a few years ago, maybe 4 years ago. But that's actually, we're starting to be able to measure all those things. The record keeping for all the rotations and the nutrient flows through the landscape and into the soil. So it's that air, soil, water system that we're actually able to start to, for the first time, really start to understand what's happening. So, and let me just give you a sense. So before I showed you some pictures of our farm, I'm going to show you a couple research plots right here just to give you a sense of what we can start to do once we take those images and put them into the software. So here are some hairy vetch plots. We were doing no-till hairy vetch into hay sod to provide legumes for the following no-till year. The left there is 3D volumetric mesh of the actual topography of the vetch. You'll see it in a second come up. That was reconstructed by taking lots of two-dimensional images and turning it into a 3D model from which we can not only get color and texture, but we can also get a volume analysis, which is going to be somewhat related to performance and quantity of biomass. Seems like it's hanging up there. Oh, there you can see it's just choppy. But so there you can see that you can very clearly pick out the vetch. And so when I'm talking about collaborative research and development, think about this as far as its accessibility, as far as what actually happened versus an academic journal, which we're publishing this data too, but it's a table or maybe you have an image. But this is something where we could send anybody to go and say, well, this is actually what happened, and you can click on it and see. I'm going to actually skip to the next. So you can actually click on that that plot and get all the associated data with that. So this is another stitched image of different tillage trials and reduced tillage trials of corn. And you can get a sense, again, the resolution, when you zoom in on that, you can look at the leaf level of these. And this is how it's reconstructed. Again, because computing powers come down, this actually doesn't happen to be open source software, but there's an open source version of this software. So essentially, free software. The challenge is the support community to make this possible. And then, because the cost comes down, it also has an implication about who does research, what research questions get asked, how they're funded, and then how the information that comes out of that is disseminated. Really changes a lot of that. So here's volumetric analysis of those corn plots, which correlated really well with the yield of those corn crops. But unlike other methods where you have to wait for harvest, we could actually sample this multiple times a year. We could actually watch crop growth rates. We could monitor weeds in the patch as well. There's 3D rendering, again, all from two-dimensional images. Now, this isn't extraordinary. You could expect this from large government research. This was, again, just to bring it back, this was done with a couple $100 UAV. And there's layering the data in such a way that you can share that data with anybody. So here, again, looking at sharing, we had a slope that was compacted. We were having some issues. We used a yeoman's plow across the slope, and I think you can see where we stopped in that slope. Darker green showing, so it gives immediate feedback. Another way to talk about it, part of the challenges with these systems is that if you don't see it, you don't believe it. And that's where the farm visits are so important. But if we can add sort of the effect of a farm visit, but even further, then I think we can add more innovation and creativity to this process. This is cover crop trials, looking at species identification from image analysis. And we can go beyond the visual spectrum. We can look beyond what we can see. That's where we're limited often in our management decisions, is we're stuck with what we can see at eye level, looking down, limited field of view, and we're limited to what our eyes can see, where we can go beyond the visual spectrum. So this was NDVI imagery, and then an image analysis to pull out the vetch and non-vetch species. We can we can pull back and look at larger context and patterns, and we can look right down and model the leaf level. So you can bring it together, and we can, like I said, we can start to answer some of these bigger questions, especially when we add in management, and we can take some of the burden off of record keeping and understand what's going on in our systems a little better. And you get feedback, management feedback from the system. So as I mentioned, it's about managing this complexity and diversity and can we apply these tools so that we're doing complex and precision ag that's highly diverse rather than precision ag that's really homogeneous. So I'll close out by saying that, by going back a little bit too, that, if you go back to in agricultural history, again, this Back to the Future, right after the fall of the Roman Republic, Finney records that the land offered nuts, her fruits in abundance. She seemed to take pleasure in being cultivated, and pulled by triumphant hands to match this honor. She increased her yield with all her might. Today, that's no longer the case. We have abandoned her to mercenaries. We get slaves and convicts to cultivate her, and one is tempted to think that she's felt this affront. So what was happening there was what we were looking at with that flip in the physiocratic tree, the capital, the expansion of empire, above care of the soils and agriculture. So capital has overpowered the land, but what the land wants is can be documented, and we can use that documentation to tell the story, to flip some of that back, so that we can build an agriculture that we're all proud of. And we can do that, I think, most importantly, by sharing and exchanging our ideas and shifting the balance of power from those who derive their power from control of information and capital to those who mix their labor with the environment and share their best ideas to improve the conditions of this great agricultural experiment that produces a system that we can all be proud of. Thank you.